In this video, we're going to be discussing arc length of a circle with a given central angle theta and a given radius length. Okay, and what we're going to do is we're actually going to start by tying it into the radian measurement of an angle in the first place. But recall that given some angle, we say in standard position, let's say we have some angle theta. Perhaps my theta is, this angle right here. We'll call this theta. Let's assume that we have a circle of radius r that is centered at the origin about this, but we say that this circle would have some radius r and that this angle would subtend some arc length here, or it would like intercept some arc length here, pardon me, s. But we say that the definition of radian measurement of this angle in the first place is the number of times that the radius fits into the arc length, the number of times that this length fits into this arc length here. So we say in general our definition for radian measurement is this right here. So your angle is only so big as how many times the radius fits into the outside. But the nice thing about having something in radian measurement is it tells you exactly how many times the radius fits into this outside arc length. So what I can tell you is this: if we were to actually say know this angle in radian measurement and say that we knew the length of this side right here, or this radius right here, if we knew this radius length, then I could really just take the number of times the radius fits into the outside and multiply it by the length of one radius, and that would give me the arc length in the first place. Or in other words, we could say that if theta is equal to the number of times the radius fits into the outside, then really what we could do is we could take both sides of this equation and we could multiply by the radius length. And what we end up with is this new formula that says if we wanted to solve for the arc length, all we really need to do is take the angle measure in radians and take it times the length of one radius length. So in other words, what this is really saying is this: if we wanted to write this out in words, we say S equals theta r, or r theta. We can say really is this: the number of radii in that arc times the length of the radius. Okay, and so in other words, we're basically saying if the radius fits into the outside this many times, let's take how many times it fits in times the length of one radius. That would have to be the intercepted arc here. Okay, and this is kind of a really nice thing. So we say for a circle of radius r and a central angle theta, which intercepts an arc length of s given by, the arc length for a circle of radius r and a central angle theta intercepts an arc length of s is given by s equals r theta. So this is our arc length formula. The important thing to remember here is this: theta must be in radians. And I want you to understand that if theta weren't in radians, if this were in degrees, it wouldn't be as effective. It wouldn't be effective at all, because really when theta is in radians, what it's really doing is it's telling us how many times the radius does actually fit into that arc length. So that's why this is effective when we have it in radians, because we could say, let's take the length of one radius and then multiply by however many of those radii we have in that arc length. Okay, so let's go ahead and take a look at example number 5 here. It says a circle has a radius of 27 inches. So we could already write that down here. We say 27 inches. And we also say this: it says find the length of the arc intercepted by a central angle of 160 degrees. So I'm going to say, well, then my angle is 160 degrees. So now again, we could go ahead and solve for the arc length by just taking the radius, the length of one radius times the angle here, but the angle has to be in radians, okay? So to kind of sketch out this situation that we're seeing here is we're saying that we have this radius length here. We say the radius in this case is 27 and it's in inches. I'll write my inches out here. And we say that we have a 160 degree angle. So 160 would be just shy of this 180. It'd be about 20 degrees shy of this 180. So we say that really this is the angle that we have right here. Okay, what we're interested in finding is this length of S, or this arc length around the outside that is intercepted by this central angle theta in the first place. So just know this: the reason why we need to convert this into radians is because if it's in radians, then it would literally tell you how many of these 27 length things would fit into this arc length in the first place. So our first step, if we're given something in degrees and we want to go find the arc length, is to go ahead and convert this measurement into radians. So I'm going to go ahead and take this by our conversion factor. We're going to multiply by pi over 180 degrees. So the first thing I'll acknowledge here is that our degrees, they cancel out. We say that we could divide both of these by 10. Those cancel out. We say, well, what goes into 16 that also goes into 18? What common factor do they have? We'd say, well, they have a common factor of 2 at least. We could say, so 2 into 16, 8 times, and 2 into 18, 9 times. We could say that this angle really is 8 pi over 9. So we say, I'll write this right here. We say 8 pi ninths is the same thing as 160 degrees. So now, if we want to solve for the arc length, what we're really saying is this. And 8 pi ninths, let me go ahead and do this for everybody that's watching this. If we were to actually find that as a decimal, 8 times pi equals, divided by 9 equals, what we're really saying is, and I'm going to write this in here actually as a decimal, even though we're going to use the exact value, we were able to determine that it's about 2.79-ish. About 2.79-ish radians. So what this is really saying is, well, if you change this from degrees into radians, really the radius should fit into this arc length about 2.79 times. So what we're really going to do is we're going to say, if I want to find the arc length, we'll take the length of one radius, which is 27 inches, and we're going to multiply it by the angle measurement in radians, which is about 2.79. Now, to be accurate, what we actually want to do is we want to leave this as an exact value here. So we're going to take 27, or 27 over 1, times 8 pi ninths. We'll do any reducing that we can do now. I actually noticed that 27 and 9 share a common factor of 9. So we say dividing both of those by 9, we get really 3 here, and this would become 1. So I don't think any other reduction can occur. We would say, well, then how many total inches do we have here? We have 3 inches times 8 pi. This would be 24 pi inches would be the distance of this arc right here. And as a matter of fact, if we wanted to come up with, it's an application problem here. So if we wanted to come up with a decimal value, we could certainly do this. We could say, let's take 24 times pi. And we could say, well, if 27 fits into this outside about 2.8-ish times, then 27 plus another 27 plus about 80% of a 27 adds up to be about 75.4-ish inches. And that's entirely within reason. So that's how many inches that would be right there. So let's go ahead and consider letter B here. We like to do a lot of problems. The establishment, the math teachers of the world, a lot of problems with clocks. I don't know why. But it says find the distance traveled by the tip of the minute hand of a clock if the minute hand is 12 centimeters long and 40 minutes have passed. So what I want to do is actually want to kind of conceive of this situation in the first place. We say maybe here's our clock, and we say that this radius is 12 centimeters in length, 12 centimeters, and we say 40 minutes have passed. So 40 minutes, 45, if I said I started here and went around this way, 45 would be like 3/4 of the way around. We say then 40 minutes would be about right there. Okay, so here's like our hand went around. And actually, if it's a clock, gee, I guess I'm being a total jerk here. Let's assume that the hand maybe started up, maybe facing 12, and it's gone around 40 minutes, so it wouldn't go quite to 45 minutes. It would make it just prior to that. That'd be about 40 minutes right there. So our angle actually has rotated this far. We don't know what this angle is, but we also actually do know that the radius is 12 centimeters long. So according to what we've already said, we could actually go find how far, at least the distance the tip of this has traveled, if we were to find this arc length right here around the edge of the clock. And we, of course, represent this with the letter S, and S is equal to the radius length times the angle in radians, okay? So we already know that the radius is 12. We need to know how many radians is in 40 minutes. And actually a really nifty way to do this is to say, well, one time around would be 2 pi. That would be one full rotation. We only went 40/60ths of a rotation. So what we're going to do is we're going to find 40/60ths of 2 pi. And remember in math, of is going to mean multiply. So we have 40/60ths of this 2 pi here. As a matter of fact, I'm going to go ahead and simplify this. We say, oops, not equals, but times, that would be the same thing as times 2/3. So multiplying these straight across, if we wanted to get our angle here, we could say that it's really 4 pi thirds, which is actually kind of an interesting number. I'm really familiar with that rotation measurement there. So we say that if the radius is 12 centimeters, and if theta is 4 pi thirds exactly, which I'm going to go ahead and get another decimal approximation here. We say 4 times pi divided by 3. We'd say as a decimal it's about 4.18-ish radians. What we're really saying then is this. We're saying that the radius length of 12 here should fit into this outside arc about 4.18 times. So let's just say this. What if we took 4 times 12? This would be at least 48. Okay, so 4.18 times 12 is going to be a little bit bigger than 28, or maybe a lot bigger. Let's go ahead and figure this out. So we say S equals theta times R. So we say theta times R. Our theta here is 4 pi thirds. The radius in this case is 12 centimeters long. I want to do this with the exact value, so I notice that let's go ahead and put this over 1 here. We notice that 3 and 12 share a common factor of 3. So 3 goes into 12 4 times. So multiplying straight across now, we get 16 pi on top and 1 on bottom. So I guess I could neglect to write that one. We say that exactly 16 pi centimeters is exactly how far it went. And just to show some reasonability here, if we were to take 16 times pi, we actually get about 50.27. Okay, so I'm going to write 50.27. We want to label this in centimeters. So this is our approximate value, but is this within reason? We say, yeah, it's totally within reason, because really what we were saying again was this. We took 4.18 of these 12 centimeter length things fit into the outside of this, and 4.18 of these 12s would be about 50.27. So that's how you determine the arc length of a circle with a central angle theta and a radius r. Cheers.